Welcome to this explainer. Today, we're diving straight into the fascinating mechanical magic that keeps an internal combustion engine alive, powerful, and absolutely protected from destroying itself.
Think about it for a second. An engine is literally an explosive, heat-generating beast, so asking what prevents it from just melting down into a solid block of metal is the perfect place to start our journey. Because honestly, the forces at play inside an engine block are incredibly violent. Without some seriously careful engineering, the whole thing wouldn't last 5 minutes.
To answer that, here is our roadmap for today. First, feeding the engine. Second, carburetors versus fuel injection. Third, the role of engine oil. Fourth, understanding oil viscosity. And finally, number 5, dry sump lubrication systems.
All right, Section 1, feeding the engine, the respiratory system of combustion. Let's explore exactly how an engine breathes and feeds to create all that horsepower we love.
For decades, engineers relied on this brilliant little physics trick called the Venturi effect to mechanically mix air and fuel in just the right ratio before sending it to the combustion chamber. It's elegantly simple, really. As air passes through a narrowing tube, it naturally creates a pressure drop. This vacuum literally sucks fuel right out of a float bowl and into the airstream. From there, jets and valves control the exact flow. It's entirely mechanical, relying 100% on the physical laws of airflow. No computers needed.
Moving on to Section 2, carburetors versus fuel injection, analog solutions going head-to-head with digital precision.
It's the ultimate showdown in fuel delivery. In one corner, you've got carburetors. They offer this beautiful mechanical simplicity. They're cost-effective, super easy to repair with a basic rebuild kit, and they are absolutely legendary for drag racing and high-horsepower builds. But, they do have their drawbacks. They can really struggle to start in cold weather or high altitudes, and they need regular manual tuning. Now in the other corner, we have electronic fuel injection, or EFI. This is all about electronic precision. An engine control unit, the ECU, uses sensors to constantly monitor throttle, temperature, and air intake, adapting the fuel delivery in real time. That means consistent cold starts, super smooth idles, and it's excellent for turbo setups. The catch? It's way more expensive and a whole lot more complex to repair if something goes wrong.
Which brings us to Section 3, the role of engine oil, the circulatory system of protection. Let's see how the engine actually survives the extreme heat and friction of those internal explosions.
If you zoom into a microscopic level, even metal surfaces that look perfectly smooth to the naked eye are actually covered in tiny, jagged defects. When two moving surfaces make direct contact, these microscopic peaks grind together. This creates massive sliding friction, robs the engine of energy, generates a ton of unwanted heat, and, quite frankly, causes catastrophic wear if left unprotected. It's the ultimate enemy of an engine's lifespan.
So, that's exactly where the engine's lifeblood steps in. The oil actually physically separates those microscopic imperfections, acting as a fluid cushion between the moving surfaces. As long as that film remains unbroken, metallic friction is entirely replaced by the internal fluid friction of the oil itself. It physically prevents metal-to-metal contact. This is absolutely crucial for parts that take a beating from shock loading, like a reciprocating engine's connecting rods.
But here's the thing. Oil is a massive multitasker. It doesn't just lubricate, it actually cools the engine, remarkably handling up to 50% of the total engine cooling just by absorbing intense heat from the pistons and cylinder walls. On top of that, it forms a vital seal between the piston and cylinder wall so combustion gases can't leak out. It even cleans the engine by carrying abrasive little particles straight to the filter. And, as a final bonus, it prevents interior corrosion by leaving a nice protective coating on the parts when the engine is turned off.
All right, Section 4. Understanding oil viscosity, the science of flow and temperature. Because temperatures shift so drastically inside a running engine, the oil's resistance to flow is arguably its most important property. Over the years, engineers have formulated very specific oil technologies to handle these wild extremes. First up, straight mineral oil. This is a highly viscous petroleum base without any extra additives, and it's mostly just used for breaking in brand new engines. Then you have ashless dispersant, or W oils. These take a mineral base and mix in non-metallic additives that suspend dirt particles so they can be filtered out, all while stabilizing the oil's flow across different temperatures. And finally, semi-synthetic multigrade. This is a high-tech blend of synthetic and mineral oils packed with advanced additives. It offers exceptional cold start protection and handles nasty engine deposits beautifully. To measure how well an oil actually handles those extreme temperature swings, engineers use something called the viscosity index. A high index means the oil resists thickening up too much in the freezing cold, which is great because you want rapid cold cranking and quick lubrication on startup. But equally important, it resists getting too thin in extreme heat, ensuring it stays thick enough to protect heavy bearing loads when the engine is running blazing hot.
And that brings us to Section 5, Dry Sump Lubrication Systems, external storage for extreme conditions. To manage all this specialized fluid efficiently, aircraft and high-performance engines often rely on this advanced setup.
So unlike a standard wet sump that just stores all its oil right down in the bottom of the engine crankcase, a dry sump system continually pumps the lifeblood out to an external storage tank. This kind of setup is an absolute game changer for complex machinery because it guarantees a massive dedicated supply of oil that's totally independent of how much space is inside the actual engine block.
So what's the actual journey of the oil here? Well, first, the supply tank safely stores the oil externally. Second, a heavy-duty pressure pump kicks in, pressurizing and circulating that oil straight into the engine block. Third comes filtration, where the oil passes through filters to ensure it's spotless. Fourth is the engine lubrication itself, where the oil cushions and cools all those fast-moving internal parts. And finally, step 5, a scavenge pump quickly sucks up the accumulated oil from the engine sumps and sends it right back to the external tank so the whole cycle can start over.
At the literal heart of this circulatory system is a gear-type positive displacement pump. It uses two tightly meshed gears spinning inside a housing. As the oil enters, it gets trapped between the gear teeth and the housing wall, and then it's forcefully pushed out the other side. This mechanical action creates the exact, relentless pressure needed to push oil through every tiny passage in the engine.
But hold on, before reaching those critical engine bearings, the oil gets pushed through a filter housing, usually a canister type with a replaceable cartridge, often made of a pleated cellulosic media. Its one and only job is to trap harmful microscopic particles like dirt or tiny metal shavings. It keeps the engine's blood perfectly clean and stops abrasive wear dead in its tracks.
So, now that you know exactly how a high-performance engine breathes, feeds, and fiercely protects itself from literally tearing its own internals apart, what's your pick? If you were putting together your own dream build, which setup would you choose? Classic carburetor simplicity or modern EFI precision? Think about it and consider all the unbelievable engineering happening under the hood every single time you turn that key. Thanks so much for joining me on this explainer, and keep learning.